Welcome, calculus enthusiasts. Today we're going to be representing the definite integral as a limit of Riemann sums. Now this is a beautiful thing because it helps us solve one of the most fundamental problems in calculus, which is approximating the area between the function curve and its x-axis. Now we can represent this using a Riemann sum, which is just summing the area of small rectangles between the x-axis and the function curve between the sum interval a to b by picking a bunch of small rectangles, like I said, and summing them up. Now, in this case, I picked 3 rectangles to represent our Riemann sum, and as you can see, our 3 rectangles has some small gaps in the approximation, and that's why it's an approximation, because assuming we pick the right endpoint like I did here, this doesn't fully represent the area under the curve. Now, this is a problem because we want the exact area under the curve. One way you could solve this problem is by shrinking the rectangles. Now, as you can see, if I draw on this diagram here and I add a whole bunch of different rectangles, like making the width of the rectangle smaller but adding many more of them, you can see that this accurately represents the width, the total area of the curve a lot better compared to the 3 rectangles that we picked before. Now, as we make those tiny widths, which we represent here in the Riemann sum formula as delta x, as they approach 0, which means we have infinitely many rectangles, but we have an infinitely small width, we can represent the entire area under the curve, because if we have infinitely many rectangles, we'll have no gaps between the curve and the x-axis. And we can represent the total area, which we can write here as we take the limit as delta x approaches 0 of the Riemann sum, we get equal to the definite integral from a to b of f of x dx, where dx is simply delta x as delta x approaches 0. So it's some infinitely small width in x.